So let's get started. What I want to do today is start off with, we kind of hastily went through the last few slides last time. So I'm just going to show you kind of the completed notes that I had here, and I'll make sure to update the slides that I have on Canvas to include this stuff, because I'm not going to really give you that much of a chance to write it down, I guess. So we'll just go through a couple slides, wrapping up 1D numerical. And then today, the rest of the time, we're going to be talking about extended surfaces, okay? All right, so where we left last time was we talked about, we had our system of equations. Remember that we're developing a set of equations for each node, or an equation for each node, which gives us a set of n equations that we have to then solve. And we went through this exercise of coming up with temperature-dependent properties, where we said, okay, conductivity here is a function of temperature, as is electrical resistivity. And so we need to accommodate that in our solution. We decided that for this problem, the best way to evaluate conductivity is at the average temperature between two adjacent nodes. Otherwise, we're creating or destroying energy, right? Resistivity, we said we could evaluate resistivity at the node temperature because that's not something that needs to be agreed upon by adjacent nodes. Okay, so going through this, you see now we're evaluating at the average temperature here and the node temperature here for each of the nodes 1, I, and then n. Okay, so we have our system of equations, but then the challenge is we're using the temperatures that we're trying to solve for as part of the properties that we need to evaluate in order to solve the temperatures, right? So it's this implicit set of equations. It's no longer an explicit linear set of equations. It's implicit. So the challenge here was not so hard. In ease, we can just plug all this in. Ease will solve, or it should solve. If you're actually doing this in ease, you might run into some trouble though. So unless you have really good starting guesses, ease will have a hard time converging. So one way to do this would be, if you're solving this problem in ease, you might formulate it so that when you're evaluating conductivity, you would first evaluate conductivity using a constant temperature, or evaluate it using just the constant part of the conductivity. So let's say you had some function, like let's say k of t was actually some function a plus b times t, right? That's kind of what we assumed up here, right? I just rewrote this. You can come in and you could say, all right, I'm going to solve this problem. I'm going to comment out in ease this part, and just solve it for k is equal to the a part of the equation, right? Then k is just a constant again, and you can solve it. And ease will almost certainly solve that problem. Then you update the guesses, go back, uncomment this part again, and now you resolve it with that much better set of starting guesses. So that's one way to deal with solving these problems in ease. Okay. The other two, we really didn't get to talk about that much, so I'll just kind of show you. This is kind of a lot of words, but what this is just the general process that we talked about and how to go about solving problems like this, where you have temperature-dependent properties or some temperature dependence, nonlinearity basically built into the equation. And so first, what we said was we're going to start off by assuming a temperature distribution, and we're going to call that assumed temperature distribution T hat. Okay, it's our kind of our guess for what we think T is going to be. Okay, we're using that guess of T. Now we set up our A and B matrices using that T hat to solve for any temperature dependent coefficients. So you're going through the first pass just using your guess for T to solve the temperature dependent properties. Then we solve the matrix, right? AX equals B. We do that matrix inversion in order to predict the actual temperatures. And then we look at the error between what we originally guessed here. Right? This is our original guess for temperature. Maybe it was just constant to begin with, or maybe some linear distribution or something. Compare that to the actual temperatures you just computed. And like I said, there's a bunch of ways to evaluate this error. This error here can be max error. It could be this root mean squared error. It could be whatever you think is the best way to get a handle on the error in the problem. And first time through, you're probably gonna have a lot of error, right? So you look at, is my error less than a tolerance? If it is, I'm done. If not, I'm going to take this whole thing, go back up, update my guess values to be my new solution, and then just repeat this process. Okay. So this is where you get into, this is what you're going to have to do for your homework, I believe. Actually, check that. You may have to do it for your homework. I'll have to look back at the solution. But what you'd end up having then is you do this inversion process and you have a while loop, which is really similar to what you see in the examples for MATLAB and what we did in lecture last time. Okay. Any questions on that process? Yeah. You do it for both. Yeah. So like anytime you're using, actually here to answer that, let's look at the next one because you can kind of see how it pans out. So if you break it down by the two different methods, you start off. So this is our equation up here. This is where we kind of started. And we say there's K as a function of temperature. Then the second step is we're going to assume some temperature distribution, and we call that T hat, right? So now we see in here, we see where we're doing the evaluation of the properties, we're using T hat. Okay, so we get to that point. Then it's slightly different depending on if it's matrix decomposition versus Gauss-Seidel. So matrix decomposition, you see here we have our temperature evaluation here happening. But we still have the kind of nodal temperatures we're trying to solve for there. So you have this whole thing becomes your AI term or the coefficient. So built into that coefficient that's going into the matrix is your temperature dependent properties that you're evaluating with your guess for temperature. So that becomes the coefficient. And then you solve that linear, what becomes a linear equation because you've guessed the temperature. You solve that using matrix inversion, right? And then you do that sort of that like looping, iterating thing on this. Okay, Gauss-Seidel, you just have to solve explicitly for some temperature, but the temperature you're solving for can be in terms of the guess temperature over here, right? So you can see the guess temperatures appearing over here, right? Is that everybody okay with that? Kind of makes sense. It is one of those things you're going to want to, you get into it, you do it, and you kind of see how it plays out. But I'll provide this slide, and you can also look back at the MATLAB examples that we went through, and hopefully that would be enough to get you started on it.